Natural physics is a concept astrophysicist Leroy Larry developed that explains in down-to-earth scenarios how the principles of physics could have come about from observing nature. Each episode begins with a scenario, followed by an example to illustrate the application of these principles in futuristic research at the frontiers of science, such as Leroy's astrophysics doctoral research, and then concludes with an exploration of how these same principles could have very well been used by ancient cultures and civilizations. Mathematics is naturally encountered and incorporated as the exciting and fun tool of science that it is. Science is the window into our amazing world of nature, and mathematics is the tool to open that window. Natural physics encompasses current, futuristic, and ancient physics, and ties them together by the principles of physics that are common threads running throughout each.
Greetings, everyone. I'm Leroy Larry, and welcome to the Natural Physics Experience, live from Costa Rica. Joining me is August Wilgemuth from Edmonton, Alberta, Canada. August, your question at the end of our last session about would a radioactive source interact with a radio source? Excellent question, August. Now, you understand how the light, the electromagnetic radiation that the radio gives off, is at a whole different frequency than the light that a radioactive source would give off, radioactivity. You understand that?
Yeah.
Yeah, it's what the radio gives off is like a motorcycle. What the radioactive source gives off is like a semi-truck, right?
Yeah.
Radio waves, gamma rays, X-rays, gamma rays. Okay, and they all travel at what speed, August? What speed does light travel at? The fastest velocity we know of in nature. How fast does light travel? 186,000 miles per second, which is equivalent to 300,000 kilometers per second, okay? Now,
Okay.
August, you saw how the light that went into Zuzu's eyes, where her eye color changed from blue to hazel green, that was different frequencies of light, right?
Yeah.
Remember that, right?
Mm-hmm.
So I thought what you might enjoy, I thought I would play a video for you that I made a while back, and it talks about light. For example, the light that we see, and it talks about the light in outer space, right? And they're connected. So I thought you might enjoy this. And it is connected with your excellent question of why or how or if actually a radioactive source that emits light at gamma ray energies, right? Remember the ocean waves? Gamma rays are the most powerful. So August, when a wave comes from the ocean into the beach, if it's a gamma ray, are the waves going to be coming in quick or slow?
Fast.
What's that?
Fast.
That's right. The gamma rays are going to be coming into the shore quick. The wavelength, the distance between waves is very short. The frequency is very fast. They come in very fast, okay? More energy. Now, August, the radio waves, which is what a radio would emit, are the waves going to be coming into the shore faster or slower than the gamma rays? Radio waves.
Slower. Slower.
Huh? What?
Slower.
Exactly. low energy, August, low energy, long wavelengths, a lot of distance, a lot of time between waves come into the shore for radio waves, right? Very slow, long wavelength, okay? Whereas gamma rays, more energy coming into the shore quicker. Frequency is higher, more energy. So I'm going to play this video for you, and I hope you enjoy it.
Has anybody here ever seen the movie Predator? Good movie from the 80s. The alien wore a helmet which allowed it to see in different wavelengths of light: optical, X-ray, infrared, ultraviolet. We may not have a helmet like the Predator, but we do have ground-based telescopes and space telescopes orbiting high above the Earth's obscuring atmosphere, which do allow us to look into outer space with different eyes that enable us to see in the different wavelengths of light. The visible range in which we see is a small part of the electromagnetic spectrum. Just as a group of 6 runners clasping arms will break apart when running from the beach into the ocean, a beam of light breaks up into the 6 major colors of red, orange, yellow, green, blue, and violet. Because these colors travel at different velocities when traveling from one medium into another. We use telescopes to extend our senses of sight and hearing, to peer and listen into outer space.
These are physics of telescopes, August. How we hear. Radio telescopes that we listen.
Optical telescopes are our eyes.
Optical telescopes are in the optical range, August, to look into outer space. Okay? All over the world, optical telescopes.
And radio telescopes are our ears.
So radio telescopes, August, we use to listen to outer space, right?
That one already collapsed.
Yeah, we talked about that one, didn't we?
We also have space telescopes that orbit the Earth.
That are above the atmosphere, August, so they can look right out into outer space.
And space probes that travel into outer space for us and go places where we are as yet unable to go.
Voyager, Pioneer, Galileo. All these eyes, August, to look into outer space.
And ears.
And ears. Excellent, August. No noses. We can't smell in outer space, right?
Yeah.
And no touch. We can't feel outer space. There's Galileo, another space probe, right, that I was involved with. Okay. And August, you pointed out an excellent fact.
This is data from the Galileo space probe. This is a view of the plasma sphere surrounding Jupiter that we obtained through the eyes of the plasma wave instrument on board the probe.
That I sent commands to.
The colors represent energy levels, and this data shows the change in energy as time goes by.
Okay.
A long time ago, in a galaxy far, far away, I was in the Boy Scouts. We went camping far away from the city lights, and I remember looking up at the Milky Way. It really did look like milk had been spilled across the night sky.
Have you ever seen the Milky Way?
I did not know
August?
it then, but I was looking
only
along
in
the galactic
pictures.
plane towards the center of our Milky Way galaxy. This is a view of the galactic plane of our Milky Way galaxy in the optical range of the electromagnetic spectrum.
And we can see, August.
These are views of our galactic plane in the radio, microwave, infrared, ultraviolet, X-ray, and gamma ray wavelengths of the electromagnetic spectrum. This
Okay, I'm going to stop right there. Okay, stop share. So August, our galactic plane, the Milky Way. Have you ever been camping, August?
Yeah.
Way out away from the city lights? And have you, at nighttime, when you look up at the sky, what do you see?
The universe.
What?
The universe full of
The
stars.
universe, right? A lot of stars, huh, August? Yeah, when you live in the city and you have the street lights and all that, it's you can't see that. But when you go way out into the country and you look up, and as I said in that video, August, I remember being about your age, being in the Boy Scouts, going camping and looking up and just seeing all those stars and how it looked like milk had been spilled out of a cup across the sky, the Milky Way, right?
Yeah.
And August, I just got to say, when you saw all those stars out there, imagine that they are like our sun. Our sun is a star. And just like our sun has planets orbiting around it, all those stars that you saw when you looked up at the Milky Way, they have planets orbiting around them. When you looked up at the sky, how many stars do you think you might have saw? Just give me a number.
I honestly don't know. A billion.
A billion or more, August. So think about it. All those stars you saw, each one is like our sun, and each one has a planets orbiting around it. So August, do you think Earth is the only planet that could have life on it? When you look up at the night sky like that and you see all those stars with the planets around it, do you think Earth is the only planet that could have life on it?
Because God only made human life on Earth and not on anywhere else. And he sent Jesus to Earth to save human beings.
Hey, I am not going to disagree with that. But August, I hope we're not going into a, a delicate area here, but let me ask you this, August. I agree with you on that. You know, human beings are unique on Earth, but let
I
me
mean,
ask,
I
no. Let me
I
ask you
guess
this.
there could be some like life form out there, but human beings is the only one who basically got saved from when God came down to earth.
Okay, okay. I'm digging this, August. No, I like this. Now, let me ask you this. For you, would it be more exciting if there might be other people, let's just say, if there's might be other people living on other planets that have their own culture and civilization, just like here on Earth, there's cultures in different parts of the earth. Isn't it cool that there's different cultures on Earth, August, right? People in
Yeah.
people in Canada, United States, Costa Rica, Africa, Asia, Russia, Australia, New Zealand, Hawaii. Isn't it kind of cool that there's different people, right?
Yeah.
Now, do you think it would be boring if everybody on Earth looked the same, were the same? Would that be boring or not to you?
That'd be boring.
That'd be boring. Okay, August. So let's take it up a couple of notches. I agree with you about humans on Earth and the miracle of humans existing on Earth with the animals. I totally agree with that. Let me ask you this. Do you think it would be exciting if someday, somehow, we found out that there were other people that lived somewhere in those stars that you saw when you looked up in outer space and saw all those stars? You think it would be kind of exciting if that was going on too?
Yeah.
Yeah, it would. August. Okay. Oh my goodness. I so much enjoyed hearing what you said. And it's so important to realize, acknowledge, and appreciate the miracle of life here on earth. Human life, animal life, all life. It's a miracle. So I get excited when I think that that same miracle of life could exist, somewhere out there, right? I mean, it would just be so beautiful and so amazing that life can exist out there in addition to here. What do you think?
That would be cool.
That'd be cool. Okay, August, I tell you what. Um, uh, do you have any questions about the video I just showed you? So you see how when astronomers look, okay, this was the experiment that was used to determine the speed of light. This is the physics experiment, August, that was used to find out what the speed of light is, okay? A laser was used, a movable mirror, a fixed mirror, a screen, a half-transparent mirror. But this is the diagram. Okay, it appears we're having technical difficulties, which is very understandable, right? All right. What I was going to show August was a little bit more details of the Michelson-Morley experiment, which determined the speed of light in the laboratory, conducted in 1887, right? Good while ago. I'm going to scroll down. This is the apparatus that was used that I previously showed as well. And I was going to read a little bit about this for August. So why don't I do it here? These are the physics equations I was going to show August that are connected with that experiment. Okay. But again, in the laboratory, experimental apparatus set up to determine the speed of light. 1887, huh? Pretty cool. All right. This is the conclusion of that famous experiment. It says Michelson and Morley measured the speed of light by observing the interference fringes produced by two beams. Okay. And let's go down to the end. Eventually, it led to the proposal by Albert Einstein in 1905 that the speed of light is a universal constant. And until someone else proves otherwise, the speed of light is the fastest that any object can travel. The speed of light, 186,000 miles per second, 300,000 kilometers per second. Okay. All right. So, wow, bummer that something happened on August's end, but hey, it's all good. So, last week we talked about the different frequencies of light, optical light, that caused us to see Zuzu's the eye, different frequencies of light that we saw in Zuzu's eye color, from blue to hazel green, from a higher frequency, higher energy, blue, to a lower frequency, lower energy, short wavelength to short wavelength to longer wavelengths, right? Those ocean waves coming coming onto the ocean. When her eye color was blue, that was ocean waves coming in faster at a higher frequency, a shorter wavelength, more energy. Then when her eye color became green, which is at a lower frequency, lower energy, longer wavelengths. Okay, everyone, let me just say this. Tune in next week. Same fat time, same fat channel. Okie dokie.